In this first sub-lecture devoted to control structures, we cover the basics, in particular the important notion of algorithm, and we start looking at specific control structures, namely the compound, also known as the sequence. The first notion to look at is the notion of algorithm. Of course, this is a term that has become very much in common use. This is actually new, and it's a sign of the success of information technology, because 50 years ago very few people knew what an algorithm was or had any idea of the word, and nowadays you hear about algorithms all over the place, for example cryptographic algorithms. Well, that's a good thing, but we need to know what an algorithm is beyond the rather general notion which is stated here. An algorithm is the specification of some computation, some process to be carried out by a computer. This is, by the way, this notion of algorithm, it's one of the two fundamental concepts of computer science. Computer science is about algorithms and about data, algorithms that are carried out on certain data, and the two aspects are equally important. Here we are concentrating on the first. Let's try to be a bit more precise about what an algorithm is. Perhaps we can start with what an algorithm is not. So here we have an example of something that is a recipe. I took it from a pack of frozen vegetables. The instructions are given in 3 languages, no less. None of them is English, so I wrote on the right a translation of the German version, which is essentially identical to the French version. That comes last. It turns out, interestingly, that the Italian version is a bit more close to an algorithm. But if we take the German version or the French version, they say pour the still frozen vegetables into 1 liter of cold water, add 2 tablespoons of oil and salt. Well, that's all. So, of course, we all understand what it means if we have to cook these vegetables. We understand, for example, that we have to heat the whole thing. But nowhere does it say so in the text. Of course, there's a picture. Actually, there are 2 pictures which tell us things like 45 minutes in one case and 15 minutes in the other case. So we kind of understand that we should heat these pots. Actually, you also understand that we have to use one pot, one of the 2. We don't need to use both pots. And we understand that the times given are cooking times. But there's a large amount of unstated information in all this. So it's good enough for someone who has already cooked vegetables before or cooked something before. It would not be good enough as an algorithm. For an algorithm, we need to be completely precise, because we are instructing an automaton, an automatic mechanism, and it's not going to guess anything or rely on experience. It's just going to carry out the exact set of steps that we will have given to it to execute. So here we have a recipe, but not an algorithm. We can define an algorithm with the following 5 properties. By the way, this is not absolutely a standard definition. I don't know of any formal, generally accepted definition of algorithm, but this is, I think, pretty much the consensus. The 5th point is not always retained. The point about termination, not everyone requires that an algorithm terminate to deserve being called an algorithm. The first property of a description of a process, if it is to be called an algorithm, is that it should define the data to which the process will be applied. I mentioned that data and algorithms are complementary in computer science, and to understand an algorithm, we must understand what kind of data it applies to. 2, the algorithm is going to be defined as a specification of steps, and it's going to be a combination of some elementary steps. And these elementary steps must be taken from a set of possible computation elements that are completely understood. So you might define an algorithm, for example, by taking as basic steps instructions of a computer at the machine level. We don't do this. It's too directed towards a particular machine architecture. It's too dependent on that particular kind of computer, be it the Intel architecture or the ARM architecture or any other, but at least the basic steps would be well defined. Usually what we do is that we take a more mathematical definition of the basic steps. Whatever we do, property 2 must be satisfied here. That is to say, we must define the computation in terms of well understood basic steps combined in a certain way. How do we combine them? That's going to be property 3. The algorithm must describe a certain ordering, or in general many possible orderings of these steps in order to yield a computation. We must define that in a particular execution, depending on the data, then step 1 will be executed first, then step 2, or maybe sometimes step 1, sometimes step 2. This must be completely clear. 4. Properties 2 and 3, the elementary steps and the ordering of these steps must be based on precisely defined conventions suitable for an automatic device. And this is the place where we insist on precision and on making sure that there is no reliance on common sense, on experience, on previous knowledge. This is completely unacceptable. We must have a completely self-contained definition of how the computation will proceed, suitable to be carried out by a computer. You know, people say that computers are intelligent. Of course, computers are not intelligent. Computers are just devices that carry out very precisely devised sets of operations, and they leave nothing to chance. Property number 5 is that the algorithm must be, for any kind of data, guaranteed to terminate after a finite number of steps. So I said this is not always part of the definition of algorithms. Don't get me wrong. If an algorithm is to be useful, of course it should terminate. And it should also terminate in all cases, although there are some theoretical difficulties involved here, which we will see when we review the notion of undecidability. But of course we want our algorithms to terminate. The only dispute there, or slight difference of opinion I should call it, is whether this requirement is part of the definition of algorithms or just a constraint that we want to add to algorithms in order to use them in practice. So this is the definition of an algorithm that we will retain. And to build algorithms, we are going to need the control structures discussed in the rest of this lecture and the following sub-lectures. You might ask, well, what has just been defined is just the notion of program. What's the difference? Well, you would be right to a certain extent. Algorithm is a notion that is not so different from the notion of program. The difference is in part a matter of nuance, a matter of spirit. Algorithm is usually considered to be a more abstract notion. We define an algorithm independent of the platform, meaning the computer and the operating system, independent of the programming language and any other such details. The algorithm is more of a mathematical notion that can be defined independently of any realization, whereas a program is written in a certain programming language and makes certain assumptions about its environment. In practice, however, the distinction tends to fade because, on the one hand, to define an algorithm, as we saw in property 4 of the previous slide, we need a set of precisely defined conventions. So we need a notation in particular. And so that notation is not so far from a programming language. And from the other side, programming languages, which used to be very, very concrete, 40 years ago, a programming language was low level and a program was often defined with reference to the workings of a particular computer. Well, today, this is no longer the case. And programming languages are more and more abstract, more and more independent from the particular kind of computers and operating systems that we have. So, on one side, algorithms need precision. On the other side, programming languages are abstract. So the distinction fades a bit. But a distinction does remain, in particular through the following two properties. In programs, the data is just as important as the algorithm. Programs are really the combination of data structures and algorithms. And second, typically, an algorithm is just one computation, whereas a program, any significant program, will contain lots and lots of algorithms and data structures. Data structures in object-oriented programming are object structures. So there still remains a need to distinguish between the notion of algorithm and the notion of program. How do we build an algorithm? Well, as we've seen, we need basic steps and we need ways to combine these basic steps. In object-oriented programming, the basic steps are few and very simple, at least very simple to describe at a good level of abstraction. We've seen assignment, replace the value of x by the value of y, and we've seen feature call. X.f of a, meaning apply to the object attached to x, the feature corresponding to f with the argument a, and of course there could be more than one argument or there could be no argument. As a matter of fact, even though I've put 3 dots here, there's not that much else. In object-oriented programming, one of the beauties of the approach is that actually what your programs do at runtime is taken from a rather small number of basic operations, of which these are the most important. So that's the first part, is basic steps. If we go back to the definition of algorithms, this corresponds to points 2 and 3. I'm sorry, this corresponds only to points 2, which is the elementary steps. And now we need point 3, that is, how do we define the sequencings, the orderings of these basic steps, these basic operations. And this is where we come to control structures. And we will use exclusively 3 kinds of control structure: the sequence, the conditional, and the loop. They are known, for reasons that will become clear in a while, as the control structures of structured programming. Structured programming being a movement of high-quality programming that first started in the 1970s. Sequence, conditional, and loop are our 3 pillars for this discussion, and our 3 pillars for defining the structure of computations, and the basic ideas are very simple. The sequence, also known as the compound, is the mechanism that enables us to specify an ordering of the form do A, then do B, then do C, in the case of 3 steps. And of course, this can be generalized to any number of steps, but any known number of steps. If the number of steps is not known, if, for example, we want to execute certain operations until we reach a certain goal, but not knowing in advance how many of them are going to be executed, then we have a loop, also known as a repetition. And the third one is the conditional, which takes advantage of the decision power of computers. The conditional, of which we have informally seen a few examples. Anytime I wrote if something, then something else, I was using a conditional. So the conditional is the instruction that enables the control structure that enables us to say, in some cases, depending on a certain condition, apply these steps. In some other cases, apply those steps. So now we are going to start reviewing these 3 kinds of control structure, starting with the sequence. In each case, we are going to take a particular tack on control structures by looking at them as problem-solving techniques. After all, when we write an algorithm and a program, we do so to solve a certain problem, and in each case we have a certain style of solving the problem. When we talk about a sequence, we say, I'm here, let's call it A, and I want to go there, C. I don't see an elementary operation, a basic step, to use the previous terminology, that enables me to go directly from A to C. That doesn't seem to be possible. What I do see, however, is the possibility of going first to an intermediate point, B, from A, and then a separate mechanism to go from B to C. So that's a problem-solving technique. If you cannot go there directly, go there indirectly. Find an intermediate goal. The conditional corresponds to a completely different problem-solving technique. I have a certain problem space with a large number, usually large number of possibilities. And I don't see a way to solve the problem that will work in all cases, but I see that there are two separate parts of the problem space. Let's call them A and C, or A and B, sorry. And depending on which case we're in, we may have a simpler problem. So that is going to be the problem-solving technique here. It's to say, let's find two or more, but a fixed number of subcases of the general case and solve the problem separately in each one of them. And finally, the loop corresponds to the case in which, again, you are at A and you want to go to C, and you don't see a way to go to C directly. You also don't see a way to go it through an immediately visible set of steps, but you see that you can get closer to C, and then a little bit closer, and then yet a little bit closer, and so on, like with an approximation mechanism in numerical mathematics, except that it has to involve only a finite number of steps in all cases, not necessarily a fixed number, but a finite number of cases. That's the loop. Now, try something and try it again. You may know the definition of madness that is attributed to Einstein, which is that madness consists of doing the same thing without achieving the results and trying it again and again. Well, maybe that's madness according to Einstein, but that's exactly what loops are about. Sometimes actually repeating the same thing will get you to the goal. First, and last thing for today's lecture, we look at the simplest of these schemes, the sequence, also known as a compound. Same thing. So it's very simple. In Eiffel, it's written in a very straightforward way. You write a number of instructions, meaning basic steps, one after the other. Instruction 1, instruction 2, and so on to instruction n. In Eiffel, you can just write them one after the other. Usually they're written on separate lines. If for some reason you want to have two very short instructions on the same line, write them with a semicolon in between. I1, semicolon, I2. The semicolon actually is not required, but it's of course much cleaner to make sure that the program is readable. In practice, however, usually there's one instruction per line. And so what does this do? It says execute instruction 1, and then execute instruction 2, and so on, and at the end execute instruction n. That is why it is known as a sequence. In looking at control structures, we also will be looking at conditions of correctness. Now, this may appear a bit abstract as we first see this, but I hope that as we go, you will understand why this viewpoint is so fundamental. So we have a number of instructions, as before, and each instruction, as we started to learn to see, is associated with a certain pre and a certain post conditions. The precondition is a property that holds before, the post condition is what holds afterwards. So we might have P1, Q1 for instruction 1, P2, Q2 for instruction 2, and so on. And so how do we know that the whole compound is correct? It's if every one of the instructions that make it up is correct. Well, the rule is very simple. It's that the post condition of every instruction must imply, the arrow is implication, the precondition of the next one, which means that if we start from P1 and execute instruction 1, then the post condition Q1 is going to be satisfied, and because Q1 implies P2, we are in the right context to start executing instruction 2, and so on. So the final effect, if all this satisfies the constraint just listed, that every P sub I is implied by Q sub I minus 1, the final result is this Q sub n, that is to say, the post condition of the last instruction. And that's it for today. That's it for this fairly short introductory lecture on control structures. We have seen the notion of control structure and the absolutely fundamental notion of algorithm. We have seen the example of a compound control structure, and we have had a first glimpse of what it takes to build a correct program. In the next sublecture, we are going to move on with some other fascinating control structures.